In this lecture, we're going to give our first and simplest technique to get a feasible solution to an integer program, or primal bound. The idea is LP rounding. That is, we're going to take our integer program, we're going to relax it to our linear program relaxation, we're going to solve our linear program relaxation, and then we're going to take the values and round them back so that they're feasible for our integer program. So to go through the algorithm, we're going to solve the linear program to get some variables x1 through xn. And then we're going to round these values, x1 through xn, to some other values, x1 tilde to xn tilde, so that these new variable values, the tilde ones, are in our lattice, and also these rounded values are going to satisfy our constraints. They're going to be inside of our polyhedron. The idea is pretty simple, but in practice, these rounding algorithms might be a little bit difficult to develop. To demonstrate the idea, we'll first go through the vertex cover problem. We should be familiar with the vertex cover problem by now. The integer program has a set of variables xv, each variable indicating a vertex is chosen or not. We have to cover every edge, meaning that xu plus xv has to be at least 1, and our xv has to be in our lattice, that is, it's either 0 or 1. Taking the linear program relaxation of this, we take the same set of constraints and the same objective value, but we change this integrality constraint, the fact that these xv's is on a lattice, to let them be any real number. After we have our linear program here, we solve the linear program and then we put the variables into a rounding scheme. Our linear program variables are going to be the xv's. Our rounded solution is going to be x tildes. To make our rounded solution, what we're going to do is take some particular vertex, v let's say, we're going to look at the x value, the linear program value, and say that if it's greater than 1/2, then we're going to take x tilde v equal to 1. Otherwise, if xv is less than 1/2, then we'll take xv tilde equal to 0. This is the rounding scheme. What we have to do now is show that this rounding scheme is going to be a correct one. That is, it's going to produce a feasible solution to our original integer program. To show that it's feasible for our integer program, we need to check two things. First, we need to make sure that our x tilde values are in our lattice. But this is clearly true. Every time we set an x tilde value, we've either set it to 0 or 1, so it's in our original lattice for our integer program. The second thing we need to check is to make sure that all the constraints are still satisfied for our integer program. In this case, our integer program had only one constraint, that is xu plus xv is greater than or equal to 1. To check that this is still satisfied in our integer program, we first note that because this constraint is satisfied in the linear program, xu is at least 1/2 or xv is at least 1/2 for every edge uv. Because this is true, when we did our rounding scheme, this means that x tilde u is equal to 1 or x tilde v is equal to 1. Finally, this means that if we look at our constraints in our new variables, x tilde u plus x tilde v is greater than or equal to 1. This means that the solution, our rounded solution, is going to be satisfied in our integer program. So, to summarize, to show correctness, we need to make sure that our rounded values lie on our lattice, which is true usually by construction, and also that our rounded variable values satisfy all of the constraints in our original integer program. In this case, there was just one, and we were able to show that our new solution did satisfy this constraint. The vertex cover rounding algorithm was quite simple, so we can exhibit another rounding algorithm with the knapsack problem. In this case, we have our knapsack integer program, which again we should be familiar with. We're maximizing the sum of the values, subject to the sum of the sizes being less than or equal to some knapsack size c. Our xi's have to be either 0 or 1, that's our lattice. To relax this to a linear program, we take the same constraint, the same objective value, and just let xi be any value that's greater than or equal to 0. Our rounding algorithm for this problem again proceeds in the same way. We take our linear program and we solve it to get some variable values xi. We then take these xi's to create a rounded solution, xi tilde. And this In this case, our rounding algorithm is going to be iterative. First, we're going to set all the xi tilde values equal to 0. Then, we're going to look through the xi values, our linear program variables. We're going to find the largest one, and then we're going to set xi tilde equal to 1, unless the sum of our sizes is going to be violated. That is, if we find a variable xi that's still positive, we take the largest positive one, we set xi tilde equal to 1, unless we're about to violate our size constraint. If we violate our size constraint, then xi remains 0. We stop when we're about to violate our size constraint, or when we've exhausted all the xi's. To prove correctness, we proceed in the same way. The first thing is we note that our xi tildes are in our lattice points, that is, they're in the values 0 or 1. This is by construction of our algorithm. The other thing we need to satisfy is our constraint, and in this case we only have one constraint. The sum of the si's is equal to c. But here, we've made it so that when our constraint is about to be violated, we don't add a variable. So by construction, this constraint, the sum of all I of si xi tilde, is less than or equal to c. This is something that we force to be true inside of our rounding algorithm, so it has to be true in our integer program. Now, finally, because we've shown that for our rounded solution, it lies in our lattice, and also it falls in our polyhedron, that is, our constraint is satisfied, this solution is feasible for our integer program, so we have a proper rounding scheme.